Hey everyone, welcome to today's Explainer. We are jumping right into an absolutely fascinating analysis from NEEM HQ today. We're looking at AI coding agents, autonomous workflows, and, well, this massive hidden problem, architectural stability. If you're building software right now, you already know AI is writing code, but the systems actually managing that code, they're breaking down in ways we didn't really see coming.
So here is the million-dollar question of the machine speed development era. Can AI generate production-quality code? The industry has pretty much answered that with a resounding yes. But the actual operational dilemma, the really hard part, is the second half of that question. Can it keep the architecture stable while doing so? Because as we're going to see, generating code and preserving a system's architecture are two completely different beasts.
Here's our roadmap for today. First, we'll hit the machine speed era. Second, the oscillation problem. Third, optimizing the wrong layer. Fourth, we'll look at the missing fourth layer. And finally, machine-readable governance.
Section 1. The machine speed era. Beyond human pace.
Look, autonomous coding isn't some sci-fi future anymore, right? It's our current operational reality. For early movers, AI is already turning out huge chunks of production code. The whole system is just faster in every single direction. Continuous integration pipelines, our CI loops, they're increasingly being designed for machine consumption, not for us humans. Linters, test runners, autofix workflows, they're all spitting out structured data for the next AI agent in the chain to pick up. Agents are literally invoking other agents. And because these feedback loops now run at machine pace, the speed at which architectural violations propagate, compound, and just totally escape review has absolutely exploded.
Section 2. The oscillation problem. Infinite remediation loops. Let's look at exactly how this breaks down. Picture this failing remediation loop. It's becoming incredibly common for teams running agentic CI. Step 1. An agent writes some code. Step 2. CI fails, maybe it's a type violation. Step 3. The agent retries and fixes that one specific visible constraint. But then, Step 4. Fixing that breaks something downstream. So Step 5, a second agent jumps in to fix the new break, but it only cares about its own local constraints. It's basically an invisible tug of war where neither side even knows the other exists. Which brings us right to Step 6, the original architectural rule, the invariant that was supposed to be strictly protected, reappears as broken. The agents literally just tear down each other's work because they only optimize locally. They don't have a durable memory of the big picture rules. We call this oscillation. By definition, it's when a system just never converges. Since no single agent holds the entire constraint space in its head, they get stuck in these dizzying, endless cycles of fixing one thing and breaking another. And MENA HQ makes a really crucial point here. You can't just blame the AI model's intelligence for this. This isn't a model quality failure, it's a fundamental systems design failure. Section 3. Optimizing the wrong layer. Generation versus architecture. The industry sees this oscillation happening, but honestly, we're trying to fix the wrong layer. Just throwing better, faster AI models at the problem, it's structurally misguided. Think about traditional code review versus agentic workflows. Traditional review relies on a human-skilled pace. The diffs arrive at a speed we can actually read and process, usually in serial workflows. But agentic workflows, they run at machine speed. They spit out these unreviewed intermediate states with unbounded iterations. The whole idea that traditional human code review can act as your main quality gate here completely falls apart. Because of that massive speed mismatch, review isn't a gate anymore. It's just an audit layer. It's a rear-view mirror. You're reviewing code produced by a process you didn't supervise, and you really can't reverse engineer the logic just from looking at the final diff. Now, review is still super valuable for design judgment and edge cases, for sure, but it absolutely cannot govern a self-correcting loop that's running autonomously. By the time it reaches you, it's already too late. Section 4. The missing fourth layer. Architectural intent preservation. So, if human review is too late and smarter models aren't the magic bullet, what do we actually do? Well, in an autonomous setup, your software delivery stack has 4 distinct layers. Right now, the industry is pouring huge, high investments into models to generate code and agents to execute workflows. Investment is also growing in CI loops to retry and repair, but think about that foundational layer at the bottom, governance. The layer designed to preserve your architectural intent has incredibly low investment. It is practically missing from modern production infrastructure. And skipping that fourth layer is a total recipe for disaster. Generating good code and maintaining architectural coherence are completely separate things. If you deploy an agent that churns out 10 times more code per hour, but you haven't laid down deterministic architectural constraints, well, congratulations, you are just producing architectural violations at 10 times the rate.
Now you might be wondering, wait, won't huge context windows fix this? Nope. Context windows are not constraints. Giving an AI more temporary memory might help it recall some local rules, but context totally degrades across sessions and multi-agent handoffs. It doesn't make a rule permanent or deterministic. If you want a constraint to stick, it literally has to be a structural piece of your infrastructure, not just a passing thought in an AI's prompt window.
Section 5. Machine-readable governance, structural infrastructure. So what does real, effective governance actually look like when you're deep inside an autonomous loop? For a constraint to be truly machine-readable, meaning it actually stops an AI from ruining the architecture, it needs 4 strict properties. First up, explicit scope. Exactly which files or modules does this apply to? Second, deterministic enforcement. It has to hard block, warn, or require human sign-off. It can't just politely suggest it. Third, a reason trace. It needs to output structured data an agent can automatically act on, not just a block of text. And fourth, precedence semantics. Clear rules for who wins when 2 constraints inevitably clash. Let's be real. Stuffing your architectural rules into a system prompt, a README file, or a RAG pipeline is just advisory text. It's a suggestion. And suggestions fall apart the second you cross multi-agent boundaries. Structured enforcement, on the other hand, is deterministic. It survives context resets. And most importantly, it stops violations before the code is even written. It operates way earlier in the loop, locking down those invariants before anything ever hits a human review queue. There's this fantastic analogy from the MetaQueue HQ analysis. Governance is becoming infrastructure in the exact same way that observability became infrastructure. Think about it. Observability started as this optional, nice-to-have instrumentation, and now it's absolutely load-bearing. Teams that treat governance as actual structural infrastructure are the ones who will have stable, autonomous systems. The teams that just treat it as advisory text in a prompt, they're going to drown in review queues full of architectural drift. So as we wrap up this explainer, I really want to leave you with this provocative thought. Take a hard look at your own software delivery stacks and ask yourself, are you building systems that generate code at machine speed, or are you just accumulating architectural drift at machine speed? Without that 4th layer of structural governance, you might actually just be accelerating your own systemic collapse. It's a massive, fascinating challenge for the machine speed era. Thanks so much for hanging out with me for this analysis, and keep learning.